All right, the long-awaited video where I explain why we get what we get for our expected counts. I will not quiz you on this, but if you want to know how we get this without me just waving my hands and say this is what it is, hopefully this video will help you out with that. So we mentioned one rule for independence in class where we said two events A and B, if two events A and B are independent, then the probability of A equals the probability of A given B, and it also equals the probability of A given not B. But there's another rule of independence. If two events A and B are independent, then the probability of A and B happening equals the probability of A times the probability of B. So if I roll two dice, the probability that I roll snake eyes, ones on both dice, equals 136. And the reason why that is because probability of rolling the first die, a 1, is 1 out of 6. The probability of rolling the second die is 1 out of 6, and I can just multiply those probabilities together. So in our chi-square test, we're assuming that our two variables are independent. So we're assuming that class standing and gender are independent. So if I want to find the expected probability of being female and freshman using this rule where we can just multiply the probabilities together, the probability of female and freshman equals the probability of female times the probability of freshman. And the probability that I grab a female out of my data set randomly, well, we have 462 total females divided by 753 total students. I could turn that into a percentage. I don't really care what it is right now. I'm just going to leave it as a fraction because we can do that. We can write probabilities as fractions. The probability that the random person that I grab is a freshman is 80 out of 753 because 80 of them are freshmen out of the 753 total people. So whatever this number is, there is a number that describes it, but we'll just leave it like this. So we have 462 divided by 753 times 80 divided by 753. It's some number. We don't really care what it is at this point. Now our expected count. If you think back to our sampling distribution of p hat, where your probability of success, let's say it's 50%, if you roll the dice 30 times, you expect to get success half of those times. We could take 0.5 times 30. We expect 15 successes. Same sort of thing here. Our expected count, our expected number of female freshmen, well, we can take our expected probability that we calculated on the previous page, and we can multiply that by our total count. So the expected number of female freshmen is going to equal our expected probability, which is this number right here, times our total sample size, which is this number. And this is why I left it as fractions and I didn't convert these over into decimals, because this 753 will cancel out with one of these two 753s, and our expected count, if we assume independence, is 462 times 80 divided by 753. Again, this is some number. We can calculate it. Not a big deal at this point. But here, so we've got three numbers in our calculation. 462 times 80 divided by 753. 462 is the total number of females, also known as the row total. So everyone in that row, there's 462 total females. 80 is the total number of freshmen, or our column total, and 753 is our total sample size. So 462 times 80 divided by 753, that is simply our row total times our column total divided by our overall total. I think we got something like 49.08. The number itself isn't all that important when we're describing this formula, where this formula comes from. But what you need to know is our expected count equals the row total times the column total. And that's where it comes from.